they're doing have any application or bearing on what you're doing? Is there any cross referencing here? They have a lot of saliva samples. You're dealing with tissue samples. You know, is there anything that can ramp this up given what those people are doing?
Yeah, so that's a very good question. So the people at 23andMe looked at a large but limited number of genes in what is called somatic DNA. That is, our body, and they look for mutations there. We are looking at it from a different thing. We're looking at the tumor tissue, and so. When we will get into whole genome sequencing, which I think is in the future for our lab, but we're not quite there because at the moment we just can't afford it. And we also, these things are not simple, right? I mean, this takes months and months and months to set up, and to analyze the data takes up to a year easily, right? So we're not there yet, but we think we're getting into genomic material probably. We'll get into that in about a year. That's when we can compare the somatic DNA, so the DNA from the rest of the body versus the tumor. And 23andMe looks at the rest of the body. That is useful, but it doesn't cover the whole picture. Would it be useful to combine the data sets? I think yes, but there are all kinds of practical issues that make that difficult. Practical, ethical issues that make that difficult.
Well, they're out. I think they're in Palo Alto. Isn't 23andMe out there?
Yeah, they are in Palo Alto.
You're in Palo Alto, so maybe you guys should have lunch.
No, once you. Yeah, once you have ethical issues, how close you are to each other doesn't matter. What I mean? Like they can't, John Smith sends saliva in. They can't tell me, man, this is John Smith, right? And this is the same as your block, so on.
But if they get John Smith to sign a waiver, they might be able to, and it's a pretty discreet group.
They may be, yeah. Yeah. And it may be interesting, okay, to if somebody would want to send us the information to see what we can do with it, right? But we are looking at the moment. We are looking at.
Well, I'm sure people would. If you want to see the reports, if you want to see the 23andMe reports, I'm sure there would be people in this room who would forward those to you. There's a tremendous amount of data on there, most of which most people can't access without help from 23andMe.
Yeah. Well, that's maybe something to think about. Now, again, you have to keep in mind, we are not geneticists. So these are geneticists that do that. We have not moved into the DNA world yet. Rob has, but on another disease. He's doing some work on breast cancer also. So, anyhow, it's a good idea, but I think we should think about that. Okay. And I think, to very different levels, these things stand on their own.
Slay the dragon.
Slaying that dragon.
I think I put it to
Good
sleep.
sign.
You just fell asleep. So, so the current study is, as I said, we're using a technology that is a variant of this high throughput sequencing, okay, where you can do the genome sequencing, but you can also do the RNA sequencing, and that is now, for which now we are not relying on frozen tissue anymore, but actually can use paraffin material, and that is a dramatic difference because getting frozen tissue, the 50 samples that I talked about before, I got from about, I would say 6 different hospitals, including Stanford. So, I mean, I had to beg to all my colleagues, could you please send me frozen samples of Leiomyosarcoma sarcoma? And just the disease is so rare, and very few people have frozen material.
Do you currently have enough tissue samples, paraffin blocks for the 300?
Yes.
Okay.
Yeah, that's the cool thing is that yes, we have it, and we can actually say, okay, we're going to use some and not the others. For example, some that the quality is not very good, well, we won't use them. With the Prosen tissue, it was dictated to us what we could do by the samples that we had.
Right.
Now we can come up with the best experiments and apply them to the samples that are.
But you have enough to draw from.
Yeah, no, we've got plenty at the moment. Yeah. All right. So how much more time do I have, actually? I don't want to get into your time.
No, man.
Yeah. All right, so let's talk about the next two projects. There's 3 more to go, but they will be shorter, okay? Or we can talk about them shorter, I guess. So this is a schematic drawing of a tumor. So a tumor is a group of malignant cells that have lost sort of like all rules. They divide when they shouldn't. They grow when they shouldn't. They can metastasize and cause all kinds of problems. Now a tumor is not only those cells. There are also blood vessels in there. There's also lymphocytes in there. There's also, of course, normal blood in there from your body, fibroblasts, connective tissue, and also macrophages. Okay, those are indicated here with this arrow in the schematic drawing. And a macrophage is sort of like the vacuum cleaner, if you will, in your body. When a cell dies and is fragments, the macrophage will come and heat it up. Okay. Yes.
What is it again? The macrophage?
Macrophage.
Yeah, the definition of it?
It's a phagocytotic cell, and it's a cell that eats up, consumes. Yeah,
Trash.
and it's a trash collector, if you will. It also plays a role in immunity, in presenting antigens and so on. But one of the major functions is to gobble up detritus, trash from the body. Okay, if you will. So, some time ago, I think it was in 2008, Cheng and Li showed that if you take Limehouse sarcomas and you count the number of macrophages in a tumor sample, that it has a direct effect on the outcome of this patient. In other words, patients with high levels of macrophages tend to do worse clinically than patients with low levels of macrophages.
Is there anything that determines the amount, or precipitates it, or enhances more macrophages?
Yes, and that is the next slide.
Good job.
Yeah, you should come work with us. Yeah, but the next slide shows that. And so, but this observation alone, and again, as I said before, like in research, you like to confirm your data, or confirm other people's data, but we've seen what you find on their data. Here, we have confirmed this data in 2 additional studies using completely different sets of patients. One from Denmark, that is this one now that Cheng and Li has just submitted, and one just with patients from Stanford, and it is confirmed. High levels of macrophages in Limehouse sarcoma correlate with poor outcome. Okay, and to address your question, Indigo Espinosa published it last year. It actually came out in 2010, I believe. The fact that a protein called colony stimulating factor 1, where scientists don't have a very good sense of humor, so all these names sound a bit weird, but it's CSF1. CSF1 is just the name of a protein. It doesn't matter, it could be called raw. It's a very important protein, so it's
I know the same both ways.
I mean, you could give it any name, but colony stimulating factor is one of the functions that was ascribed to it in the beginning. It does many more things now. And it was shown that by this work by Indigo, that tumors that have a lot of macrophages tend to be those tumors where the tumor cells make this CSF1.
In the pathology report, do they normally test for the
No,
CSF1?
this is all research still.
This is new stuff.
Yeah, this is new stuff. Yeah. So, but another way of doing it in an indirect way is you can just count the number of macrophages. You can stain macrophages so that they light up brown. You can stain them with an antibody, and you can just count them. And if it's above a certain level, then that tends to correlate with aggressive behavior. The mechanism behind it, we believe, is that the CSF1 is made by some, but not other tumors, that attracts macrophages in there. tumor cells, here. It gets secreted, it attracts macrophages. The macrophages and maybe CSF1 together make that there will be more blood vessels, and that affects the tumor cell to grow better.
So angiogenesis inhibitors, do they
Right.
play a role for people who have a high level of macrophages in the tumor?
That's a very, very good question, and I think it's not known. And so the thing is that angiogenesis inhibitors have focused for the most part on VEGF, vascular endothelial growth factor. And in the animal model that I mentioned earlier, that's not our work, it was shown that if you stop these inhibitors for VEGF, the tumors grow back with a vengeance, so they have a rebound effect. They didn't find that effect when they used CSF1 inhibitors in this mouse model. Here we now have a human tumor, leiomyosarcoma, where we think we have good data to support that there is a role for CSF1 in getting more macrophages and more vessels. And so what we're saying in this paper here is that we believe that CSF1 is a novel therapeutic target in leiomyosarcoma. Now, there's many papers that come out all the time. People make statements like that. So it is our task is to confirm this over and over again in a different system, looking at it in a different way. So one of the things that we're going to do is to use mouse experiments, growing cell lines in that, and inhibiting CSF1 and looking at the effect.
Are there any drugs out there right now that do inhibit
Yes.
CSF1?
There are drugs in prototype. There are no drugs on the market.
Trials, clinical trials for this?
Not that I know of. But they are talking about it. Okay, because CSF1 is, well, yeah. But I mean, it takes a long time to set up a clinical trial, and for a company, it's very difficult to decide which trial to do, which trial not to do, right? Because it's so incredibly expensive for them. So, what our role is to keep finding out more about this, specifically in leiomyosarcoma, and then hopefully get that started as a trial, either in leiomyosarcoma or elsewhere, and be involved in that, and then say, okay, you found that it now works in this tumor, but we have a tumor here that also relies on CSF1. You should try it here as well. That's what I hope is going to happen. And this is sort of like in contrast to the gene expression profiling study, which is a many year project and very large and extremely expensive. This is something that I think is much more applied, and therefore I'm very happy, to be able to do this through support from you guys, because I think this is a much more direct, goal. So this third project also involves macrophages. We've talked about the right-hand side of this thing. Here you've got a macrophage. It has something to do with angiogenesis. We don't know the specific pathway yet, but we're working on that. And that